So data link layer. So we spoke about the physical layer previously. Then I think we did numbers and numbering systems, didn't we, on Monday? So as I said, we're moving up the layer stack now. So we're doing layer 2, data link layer. So we're going to talk about that. So we're going to explain how media access control and data link layer supports communication across networks. And so we're going to talk about the purpose of the data link layer. We're going to talk about what topologies can be created or within both WANs and LANs that are based on the data link layer and the data link layer frame format. Just a basic one, not a... Okay, so the purpose of the data link layer. So it's responsible for communications between end device network interface cards. It allows upper layer protocols to access the physical layer medium and encapsulates layer 3 packets into layer 2 frames. So remember again that we're very picky about the terminology in the Cisco world, so we need to remember what packets and frames mean. It also performs error detection and rejects corrupt frames. So basically the data link layer makes the physical layer reliable. So when it comes to the 802 standards, which of course are from the IEEE, so local area network, and MAN is metropolitan area network, so often very similar standards. And so there are different standards specific to Ethernet, wireless LANs, and personal area networks. Now, when we spoke about the OSI model before, it was created, probably 25 or more years ago. I can't remember the date now. Of course, it was done by the International Standards Organization, and that's a committee of committees, so sounds like good fun. And apparently at that meeting, there were 2 camps. There were a group of people who said there should be 8 layers, and there was another group of people who said there should be 6 layers. And so that's how we got 7 layers. It's called compromise. Now, my suspicion is that the IEEE was in the 8-layer camp, because the first thing they did after that was they split the data link layer into 2 sub-layers. And so there's logical link control, which is basically the stuff that gets done for all layer 2 protocols, and they've just put it all in one spot. They've written it once, and pretty much leave that alone. And then of course there's the different MAC or media access control layers, which are for the various technologies. And so what needs to differ between Ethernet, wireless, and Bluetooth, they've made that layer different, and so, or sub-layer. And so that's why they've done it, just so that they don't have to reinvent the wheel every time they do a new protocol for the logical link control. It's there. All they have to do is interact with it, job done. And so it's just a smart modular way of designing things, and that's one of the major advantages of having a layered setup, is that if something needs to change, well, you can change that layer as long as it interacts with the layers above and below, all good, like IPv4 being turned into IPv6. Okay, so providing access to the media. Packets exchanged between nodes may experience numerous data link layers and media transitions. At each hop along the path, a router performs 4 basic layer 2 functions, and so it accepts a frame from the network medium. So of course, a whole series of bits are arriving. It has to receive those bits, record them, and wait for the entire frame to arrive. Once the entire frame has arrived, it then looks at the header information. So do I need to deal with this? That's the first question it will ask. And so what's that destination MAC address? Oh, that is for me. Okay, I do need to deal with it. And so then it will also, of course, use the error checking code to make sure that that frame is still valid. It hasn't got any errors in it. And then after that, you basically it will pass it up to the layer 3. And so, of course, when layer 3 on the router looks at it, of course, the destination IP address in all likelihood will not be for the router. It will be for a web server on the other side of the planet or wherever it might be. And so the router will go, okay, I just need to forward this packet. And so it will, of course, do its rating table lookup, decide on what exit interface it needs to send that packet on, and then from that, well, layer 2 is running on that. And so then it will start re-encapsulating that packet into a frame for that new link. And so it might be another Ethernet, it might be something completely different. And so, of course, it encapsulates it in the new frame with possibly new addressing and all that. And then it's ready to give to the physical layer to start creating that bit stream to go on its next step along the way. So that's what routers do as a hop. All right, so the data link layer standards come from different organizations. And so when it comes to LAN standards, they pretty much all come from the IEEE, Institute of Electrical and Electronic Engineers. When it comes to the WAN standards, so of course these are data that of course moves through a telecommunications network, and so it's the ITU, the International Telecommunications Union, that create those standards. And then ISO is sort of more of an overarching look, and ANSI has certainly had some involvement. I don't think it's been a lot though. All right, so what topologies can we have? So the topology of a network is the arrangement and relationship of the network devices and the interconnections between them. And so there's two types of topologies when we describe networks. There's a physical topology and a logical topology. The physical topology shows physical connections and how devices are interconnected. So it tells you where the cable runs. It plugs into that port of that device, which is positioned there, and so on and so forth. And so your physical diagram will often be a plan of the building, and it will actually have a diagram of what's plugged in where. So with a logical topology, it's more about how things are organized. And so it identifies the virtual connections between devices using device interfaces and IP addressing schemes. And so, when you have different hosts all on the same subnet, they'd be grouped together in that logical topology, even though they may not be in the same room or anywhere near each other on the same building. And so that's all about the logical design. Now, when it comes to WAN topologies, the major three options are point-to-point, hub and spoke, and mesh. Now, point-to-point is the simplest and most common WAN topology. It consists of a permanent link between two endpoints. And so, you've got a main office and a branch office, and so there's a link between them. Now, hub and spoke basically means it's a bigger company, and so you've got one central site and several branch offices, and so, of course, each branch office directly connects into the main office, and so that's your hub, the main office being the hub. That's all very fine, but there can be some reliability issues. So you got your central hub here, all of your branch offices out there. And so, of course, if that link breaks, well, this branch is broken off, isn't it? And so there's no redundancy in a plain hub and spoke. And so a mesh network, or at least a full mesh network, is there's a direct link between every site and every other site. And so, of course, here we need that link there, that link there. This one, we need that link there. And so basically every site has 4 links because there's a total of 5 sites. It needs to connect to the other 4 sites. So that, of course, if that link fails, well, hey, we've got many options for what's the best hop next, basically. So things will continue working. Of course, the downside is it's expensive, and also it makes management a little bit more difficult because basically there's all those different links you need to manage. So what you might do, let's go back to a basic hub and spoke again. You could maybe just put in one spare link on each site. And so then if any one link fails, you've got a backup link and it's not costing you a fortune like the full mesh does. So that's what's called a partial mesh. So hub and spoke is your minimum, but of course hub and spoke does not have redundancy. Now point-to-point topologies directly connect two nodes. The nodes may not share the media with other hosts. Because all frames on the media can only travel to or from the two nodes, point-to-point WAN protocols can be very simple. There's no need for addressing. And so, you know, because if it's not me, it's them. It's pretty easy to know who it is. And so Ethernet, of course, there can quite possibly be hundreds or thousands of hosts. You need to have a unique MAC address. But for point-to-point WAN links, there's only two people on the link, so it's not complex. All right, so the LAN topologies that are possible. Now, pretty much everything these days is star topology, because basically the center point of that star is a switch. And so, of course, that's where all the hosts plug in. Now, a star topology is just one switch. An extended star topology means you've got more than one switch that are hooked together. And so, so that works well. Ethernet switching is a pretty damn good system these days, and so, you know, there's not too many problems with it. Now, there were some earlier legacy topologies, and so back in the dark ages there used to be bus topologies, and so when it comes to Ethernet, there was two versions of that. There was thin and thick Ethernet, so that was the coax cable. And I think I might have mentioned that with the coax, you often had, you know, a T-piece behind each PC, and then you just basically put a bit of coax between each PC. And then at either end, as you can see, this oval bits is a terminator. And so that terminator is basically just a resistor, and it stops the signal when it hits the end of the line from bouncing back and disturbing the rest of the signal. And so I'm going to say it did work. You know, with twisted pair, you can get a maximum of 100 meters out of it. With the thin coax, you could actually get 185 meters from memory. With the thick coax, you could actually get 500 meters out of it. Now, the downside, of course, is that it's a shared medium, so there can only be one station transmitting on it at any one time. So that was a bit of a downside. Another downside, if you had a break in the cable somehow through, you know, damage or someone accidentally disconnecting it or whatever, you didn't have one network anymore. You had two incorrectly terminated networks. And so, sadly, bus networks were an all or nothing type solution. It either worked or it didn't, and there was no indication where the problem was, because the entire network would be down if there was one break. It didn't give you any hint where it was. And so, I don't miss bus networks. I actually used to support one when I worked at a high school last century as the support person, and I think there was a student who had great fun in, he just, I at one stage thought he must have run a book on how long it would take for from the time he broke the network to see me crawling around trying to find where the problem is. Of course, after a few times I thought, well, it's going to be near this guy. But anyway, so yeah, the reliability and fault finding for bus networks was pretty poor. Now, ring networks, often called token ring, weren't a bad system. Now, most of the time, the actual ring was actually created inside a box that looked very much just like a switch. And so you would plug your host in using, you know, an unshielded twisted pair or shielded twisted pair, much the same as we do with Ethernet. But basically, inside the box, there was a token, and it would pass it from host to host to host to host. And you could only transmit on the network when you had that token. And so when you finished transmitting, you'd pass it to the next host and away to go. And so it was a very deterministic way of figuring out who could transmit data. And so it was actually very efficient. The downside to it was it was designed by IBM. That's not necessarily a downside, except for the fact that them, a bit like Apple, they always want their licensing. And so it made the equipment more expensive. And so, yeah, the cheaper standard survived, Ethernet, even though at the time it was not as good. Now, half duplex opposed to full duplex communication. So half duplex means traffic can go in both directions, but only one direction at a time. So if anyone remembers the Southern Expressway 10 years ago, that was half duplex. And so, yeah. So you know, in the mornings you could drive to town, in the evenings you could drive away from town. It was duplex, it was half duplex. So that was a road, of course. When it comes to networks, basically it means there can only be a message going one direction at a time. If there is a message going both directions, it means we've had a collision, and that's bad. And so that's actually how you figure out there's an error. And so hubs ran at half duplex. Also, bus networks run at half duplex. And so, so you've just got to keep, so only one host can transmit at any one time on those half duplex networks. So it makes the bandwidth shared by all hosts. Now on a switch, you can have full duplex communication. And so you can have hosts on either end, or a host in the switch, transmitting over the same cable at the same time in both directions. And so it doubles your bandwidth, but also you don't have to share your bandwidth. So if it's a fast Ethernet, you've got 100 megabits in both directions and can be used at the same time. And so you need Ethernet switches for that to work. And so basically, half duplex is not the desired solution. Thankfully, it's a long time since I've seen a hub. They're pretty rare these days. So I moved house more than 10 years ago now, and I was packing up and hubs. Oh. Toss it in the bin. It's not worth moving the house for that. Now, there are the access control methods. I think I may have hinted at these before. And so when it comes to Ethernet, the method used by that is called Csma Ca, and that is, it's an acronym, of course. It's Carrier Sense Multiple Access Collision Detect. And so with Ethernet, basically the carrier sense means, before you can transmit, you must listen to the network and see if anyone else is transmitting at the moment. So that's what the carrier sense means. Multiple access means that if no one is transmitting, or anyone who wants to transmit can transmit then. Of course, the downside of that multi-access means that at some stage, more than one host might decide to transmit at the same time, and you'll have a collision. And so we need to be able to detect collisions and then recover from them. And so when a collision happens on Ethernet, the workstation that detects it actually sends out a jam signal, which is a special signal saying, hey, this data is corrupted, ignore it. And then the hosts that have had the collision will then need to wait a random amount of time before they try to transmit again. Now, this is only really important on those half duplex networks because you can only have one workstation transmitting at any time. On full duplex, it's actually pretty much irrelevant. So this is a little bit historical, as it were. But anyway, now when it comes to wireless networks, it's Csma Ca. And so the CA stands for collision avoidance. And so it's just a little more polite. So it's still carrier sense. You still need to listen to the network as anyone else transmitting. Multiple access means, well, if no one's using the network, anyone can transmit. But the difference is with collision avoidance, before a host actually does transmit, they actually send a request to send message to the access point saying, hey, is it good for me to send at the moment? And then the access point will either send a clear to send or no, or a negative acknowledgement. And so because with wireless, the bandwidth is that bit more restricted, they took on a more careful approach. Okay, now, deterministic access is where each node has its own time on the medium, and that's what I was talking about with token ring, is you can only transmit when you have the token, and so once you finish transmitting, you pass it on to the next host and then they can transmit. Now with Ethernet, back in the old days with hubs, if your network utilization was over about 30%, you knew you were going to be in trouble, that there was actually going to be too many collisions and things weren't going to work efficiently. While with token ring, you could actually get 100% utilization and you think, oh, well, that network's a bit busy, but there's actually no problems. Of course, now that we've got switch-based Ethernet, it's much the same in that you can get to 100% utilization, and you think, well, we might have to up the bandwidth, but there's no collisions, and so it's not going to scream to a tragic halt like it would have in half duplex mode. Okay, so I've pretty much described CSMA CD and CSMA CA. So a data link frame. So data is encapsulated by the data link layer with a header and trailer to form a frame. A data link frame has three parts. So a header, the data section, and the trailer. The fields of the header and trailer vary according to which protocol we're talking about. The amount of control information carried within the frame varies according to the access control information and logical topology. So we've got a diagram here. So basically the basic structure is header. Now the data section is basically, this is layer 2. We're talking about a frame. And so the data for a layer 2 frame is actually a layer 3 packet. And so that's your IP header, and the data and everything else is just the data section of layer 2. And so, and then of course the trailer is normally used for error detection. Now different layer 2 protocols have different methods. Some actually have a start of frame and a stop, and so it's actually the flag, they call it, the start and stop flag. And so it's normally just a special bit pattern that says, hey, this is the beginning of a frame, better take notice, there's a frame coming. And then the frame stop flag says, all right, well, that's the end of the frame now. And so some protocols will do that, some don't. Some might have a starter frame, and then they might have a field inside the header saying, well, this is the length of the frame, and so they don't need that stop frame flag. Addressing, again, depends on the protocol. So, of course, Ethernet and wireless do need addressing. Point-to-point protocol does not. And so the type basically describes what layer 3 protocol is moving this frame, and so that'll be the typical selection, I suppose, would be IPv4 or IPv6 these days. It used to be things like IPX and other such things as well, but they're much gone now. And so control, basically other information that controls the link. Of course, then there's the data section, and then there's the frame, what's often called the frame check sequence is used. And so, of course, basically, before the frame is transmitted, they'll do a calculation on the frame saying, all right, this is, they'll do a calculation and store that as the frame check sequence. When it arrives at the destination will do the same calculation and then compare its result with what was sent with the frame. And so if it's the same, no data has been modified, and so there's no errors, so it's all good. Now, layer 2 addresses, also referred to as physical addresses. I've got to admit, I prefer to call them MAC addresses because physical address sort of implies physical layer, and there's no addressing in the physical layer. But anyway, so of course, the MAC address is contained in the frame header, used only for local delivery of a frame on that link, and updated by each device that forwards the frame. So basically, if you've got PC1 sending a message to this web server, of course, the source IP address will be PC1, the destination IP address will be the web server. But the destination MAC address will not be the web server, it will be router 1. That's so that the switch on this network knows to forward it to router 1. And so also when it arrives at router 1, as I said, it looks at that destination MAC address and says, is this my problem? Oh, it's my MAC address. It is my problem. I need to deal with it. And so that's how the frame gets to the router, is by having that MAC address of the router as the destination MAC address. So of course, once it arrives at the router, it goes through that process I described a few slides before. MAC address is for me. Oh, okay, IP address it's not, so I need to forward to that network, router table lookup, then re-encapsulate. And so in this next hop, the source address will be this NIC's address. The destination address in layer 2 will be this NIC's address. The IP address will have stayed the same. That won't have changed. It's just the layer 2 source and destination will have changed. When it gets to router 2, again, it will look at it. Oh, that's my NIC address. I need to take notice. And then it will actually, of course, do the full, routing table lookup and go, oh, I'm directly connected to that network. So I can send that to the web server. And so this is the only frame that will actually have the web server's MAC address as the destination. So only the final hop will have that. Now, Lan and Wand Frames, the logical topology and physical media determine the data link protocol used. So Ethernet, 802.11 wireless, point-to-point protocol, Hdlc, and frame relay are all options. So Ethernet and wireless, of course, are your LAN standards. These are your WAN standards. Does anyone remember dial-up modems? Do you remember what protocol used to run across that? Layer 2. It was point-to-point protocol, so triple P. And so the beauty of triple P was it was really good for the internet service providers because it also built in authentication. And so when you typed in your username and password before you connected, it was actually triple P that looked after the authentication. So, well, here's my username and password. And so that's exactly what the ISP wanted. And so it worked beautifully. Hdlc is basically an older version of point-to-point protocol, but it didn't have authentication. And another problem with it was it could only handle one layer 3 protocol at a time. And so triple P is a little smarter, a newer version of Hdlc. So high-level data link control, that actually goes back to the 70s or maybe even 60s. That was an IBM standard that got standardized. Now, frame relay is actually what businesses often used to use. It was actually, you could buy virtual circuits for frame relay, and so that was very good for joining a head office to multiple branch offices. It was a very good protocol for that. And so addressing isn't required in point-to-point protocol. Addressing is not required in Hdlc because they are both point-to-point protocols. Frame relay actually does need addressing because you can have multiple virtual circuits running over the same cable. You need to identify what virtual circuit each of those frames belongs to. And so that does have addressing because it's a little more complex. Of course, the LAN standards do have addressing. Okay, that's enough for that. We'll just go through what we spoke about today. So the data link layer of the OSI model, layer 2, prepares the network data for the physical network. The data link layer is responsible for network interface card to network interface card communications. The IEEE 802 standards for both local area networks and metropolitan area networks consist of the following two sublayers: logical link control and media access control. And so, of course, that logical link control is, common to all of their protocols. That's stuff that happens for everything. And then the MAC layer is specialized for what technology it's going over. The two types of topologies that we use for networks are physical and logical. So physical is, of course, where each device is, what port it's plugged into, what cable, all that kinds of stuff. Or logical is more about how the systems are organized. Three common types of physical WAN topologies are point-to-point, hub and spoke, and mesh. Half duplex communication, exchange data in one direction at a time. Full duplex is both directions simultaneously. In contention-based multi-access networks, all nodes are operating in half duplex. Examples of contention-based access methods is CSMA CD for Ethernet and CSMA CA for wireless. Data link frame has three basic parts: header, data, and trailer. So the fields in that would be the frame start and stop flags, any addressing if required, the type of data that's being moved, any other control information required, the data section, and then the error detection field. Data link addresses are also known as physical addresses. As I said, I prefer to call them MAC addresses. Data link addresses are only used for link local delivery of frames. And there would be the logo. All right, so that's chapter 6, and so we'll get on with chapter 7 shortly.